Hi, my name is Michel, and in this video I will give you a short introduction on the benefits and challenges of parametric design approaches in structural engineering. Let's get started by looking at some of the most renowned international examples from the built world. The term parametric design is probably familiar to most in the context of famous architecture projects with complex geometries. When looking at such structures, one realizes that they would not have been made possible without the help of state-of-the-art digital tools. In the parametric design of structures, geometric properties such as curve radii, grid spacings, or even floor heights can be defined as variable over the course of planning. In other words, they stay malleable as the design progresses. However, this not only has great advantages for architects in the context of form finding, by extending the parameter list with structural properties such as loadings, materials, and cross sections, it also allows engineers to become more efficient in their work. So let us begin with a simple example of a truss system. In the conventional approach of design, we are usually confronted with geometries that are already more or less fixed. We build a structure calculation model for the desired system in our programs and optimize it from a structural point of view. However, if important geometric properties such as the span change later on in the project, the work must be carried out again from scratch. And this is exactly the point where the benefits of parametric design kick in. If the engineer now changes the geometry or the cross-section of the elements in the program, the structural analysis is performed and results are updated in real time. One can then go and optimize the system by changing the geometry. In the current example, we are deleting all the elements that don't take any loads and thus reduce the structural mass. We can also change the configuration of diagonals to further optimize our structure. One can go further in the next step and let the cross-section optimization be carried out by a structure calculation program. This means that the engineer only manipulates the geometric properties of the system or the loads and leaves the live optimization of the cross-sections to the program. This has the great advantage of quickly finding optimal geometries and comparing variants. The optimization process can then be taken to such an extent that we leave the variation of the geometry to the program and let him search for the optimized configuration with the help of machine learning. In this so-called generative design, however, it is particularly important to precisely define the input values that the program uses for optimization, and also to clearly define the objectives the program seeks to optimize. In the current case, the program searches for the solution with a minimized mass by varying the truss height and number of diagonals. As the use of these digital programs suggests, they can also be directly integrated into other areas of everyday structural design work. In this case, we have directly linked our truss system and thus the result of the parametric optimization to a BIM model. Through a continuous data stream between the two programs, changes in the design are directly applied to the CAD program as well. By this way, we are able to reduce the error rate in the coordination between engineers and drafters. So much for theory. In the following, we would like to give you some insights on the projects where we have used the advantages of this approach. The first one is a timber roof structure for an indoor swimming pool. As variable parameters, we have defined the number of shed elements, their inclination, and the number of diagonals inside the trusses. The main optimization objective here was again the total mass of the structure, but of course it is also possible to do multi-objective analysis by also looking to minimize the number of connections, for example. The program then ran through thousands of different configurations by using machine learning to calculate the optimal configuration of the aforementioned parameters. The solutions calculated in the previous phase are then sorted according to the optimization objective. The next step is for the engineer to weigh up the individual proposed solutions against each other. It is important to understand here that the human aspect will always be part of the design process, because it is the engineer who evaluates the solutions with regard to different aspects together with his planning partners like aesthetics, constructions, etc. So digital tools should therefore always be considered as an aid rather than something that will replace our work. Parametric design even allows us to automate entire digital workflows. We can provide direct rendering for visualization of structures with clients or architects. We have the already mentioned BIM interoperability for coordination purpose, and it also allows us to exchange your data with other structural calculation software for verification or in-depth analysis. We can also directly link the data stream to a carbon footprint database in order to evaluate the choice of materials and geometries. In another example, we use the parametric design approach to design a wooden pedestrian bridge. In addition to the core geometries, such as the span, width, and height of the structure, we have also defined the configuration of the truss diagonals, the pre-cambering, or even the roof shape as variable over the design process. By varying these parameters, we then designed, calculated, and presented three different variants to client for selection. So, if you're interested in getting a deeper insight into the topic that we just presented above, we would like to invite you to come to Forum Da Vinci in Luxembourg City on November 25th, where we will present some other projects where we apply this method and where we will go much more into detail about the workflows that we just presented. Thank you.